Hi, so today we're going to be talking about the k-means algorithm. The k-means algorithm is like for one of those algorithms when you don't have labels on your data. So it's an unsupervised algorithm. And what it does is it pretty much clusters your data into like little circles. Like as you can see here, it clusters it into red, yellow, and green. So as the name suggests, all you need are k-means, right? And means is exactly what we usually define it as in like k averages, right? So what do these averages mean? These averages mean like the average of the points. So if you have like 2 points on a line, like here, like -1, here you have 1, it will be -1 plus 1 over 2 is equal to 0. So then the average will be right here, right? So it's like the middle of all of the points that it's assigned to. So why does this say k averages or k means? So k is a variable. K is a variable. And k is a variable which is the number of means you have. So as you can see here, we have 1 average, 2 average, 3 average, right? So here, k is equal to 3. So the objective of the algorithm is to find these k cluster means such that it's like the best representation of the data, right? So an issue here is that we don't know which point, let's say xn, right? So x is like a data point, belongs to which cluster, which we call as zk. So for example, this point right here, this would be say x2, and it belongs in, let's say this red. This red is z1, so the first cluster. So the second point of our data set is in the first cluster, right? But we don't know that. If we had the data to say like which cluster belongs in which, then we would be done. We don't need this algorithm, right? But because we don't know that, we have to kind of solve for it ourselves, right? Okay, so I'll just give a brief overview about how to do it, and then we'll explain like why we do it. So the algorithm is like a 2-step process. So first, well actually it's 3-step, but we'll just say like 1.0 is initialize your clusters. Initialize your clusters randomly. Right. So what does this mean? So you pretty much put the clusters anywhere on the grid, right? And then you just start the algorithm. And we say 1.1 is when it actually happens. And that is when we assign points to its closest cluster. Right? So pretty much if a point x1 was here and a cluster z1 and a cluster z2 was here, right? You could see that the distance between this is shorter than the distance between this one, right? So in here we're talking about the Euclidean distance, which is like x squared plus y squared square root is equal to d, right? So the distance between d1 and z1, say this is d1 to z1 is equal to 1, right? And here d1 to z2 is equal to, say, 2, right? So then we would say that x1 is in the cluster z1. Okay. Like we can use different distance measurements. Like you can even use the Manhattan distance, which is actually just x plus y is equal to d, right? But I mean, both of these are kind of like whatever. You can use them whenever you want, but that's the general idea, which is like the idea of closest cluster, right? Okay, so now that we have the first part done, now we have the second step, and the second step is recompute your mean, right? So recompute mean. Okay, so what does this mean? I'll draw a simple diagram to kind of show what is going on. So if you imagine that you have a cluster here, and then you have some points around it, right? And say that first, this cluster, when we initialize the points to its closest cluster, this point belongs to this cluster, right? Obviously, this point has to contribute to the average distance, right? So the average distance after we recompute will look like this. 2, 3, 4, and then it'll look somewhere here, right? So then before it was here, so it moved over here because this is the new distance, right? So so then you do this over and over and over again until the points, the centers no longer move a lot. So when they don't move a lot, that just means that the algorithm has ended and you've arrived at some like reasonable cluster endings. One thing to note is that depending on where you initialized your clusters, you're going to end up with different results. Because if you put 2 points really close to each other, they'll move apart really quickly in different directions. But then if you put them in different orientations, then they'll bounce away in different directions too. A good way to kind of solve this problem is by actually using this approximation algorithm from the NP-complete chapters, which is pretty much you take, say you have initially your data set looks like this. What we do is we first initialize our first cluster to be somewhere near 1 point, so here, right? And then our second cluster will then be to the farthest distance away from this cluster, that is at another point. So say like at this point, right? And then we do this iteratively, so then the third one will be here, and then the fourth one will be here, right? And then after we're done, we started off with some very reasonable distances between each other, so then they'll converge at a faster rate. So the order looks like this. First you have this, then you have this, then you initialize this one, and then the fourth cluster will be here. This initialization algorithm is called k-means plus plus. So say you have say different like shirts and different people that wear those shirts. You don't really know exactly what the shirt sizes are, but you just know that there are a group of people who are, say this is their height and this is their weight, right? You know that these, I mean, like intuitively, you know that these have some correlation, right? Because the taller they are, the heavier they are, right? Okay, so then we have some points that look like this. If we just synthetically kind of generate this data, right? Now you want to know, say 3 shirt sizes, right? So you want a small, medium, or large shirts, right? And you don't know where to kind of put your clusters of small people, medium people, and large people, right? So then you say your K here is equal to 3 because you want 3 clusters. Then using like a k-means plus plus algorithm, we can start the clusters like randomly here, right? And then the second one will be here, and then the third one will be here. So 1, 2, and 3, right? And then after they converge, I'll draw this in green. They'll probably look like this is 1, this is 3, and this is 2, right? Because that's a more accurate representation of the clustering here and here, right? Okay, so this is one application for it. Now we're going to talk about the proof on why this is going to work and why it will guarantee a local minima, at least. However, before we talk about the proof, we have to talk about a more general version of the k-means algorithm. So right now, we're just going to write down what we are trying to express with the k-means algorithm. But first, we have to say we assume that the points are going to have their respective clusters in their answer. So what we have here, the setup is that we will have x1, x2, xn data points, right? And we're going to have their respective clusters. So z1, z2, zn, right? So x1 belongs in cluster z1, x2 belongs in cluster z2. Like maybe z2 is equal to z3, for example. If x2, x3 belongs into a certain cluster, right? Okay. So then what we have is that, we have a distortion measure, which pretty much measures how inaccurate our clusters are, given that we already have these clusters, right? So we're going to first start with a variable called gamma nk is like the nth data point with the kth cluster, and this is going to be a 1 if xn is in cluster k. That makes sense? And it's going to be 0 otherwise. Right. So this is pretty much saying which cluster does the specific xn belong to. Okay, so our distortion measurement will look like this. We sum up from n is equal to 1 to n. Actually, I should say n here. Okay. And then we're going to sum up over all the clusters. K is equal to 1 to k. K clusters, right? K means. And then we're going to have the membership of that specific point times the distance. So this is going to be the distance between xn and mu k. So mu k here is the center of the cluster. So this is the average. Right? This is the point where the cluster comes out from. And usually we express the distance measurement by the x squared plus y squared is equal to d, right? So what we're going to do here is just say it's going to be the norm, which is pretty much that, but in like higher dimensions. So it's going to look like k1, k, gamma y, k, and then now this is going to be the norm of xn minus mu k squared. So what we want to do is to minimize the distortion measurements, right? And usually when we minimize something, it's like taking the derivative of a function. So for example, if it looks like this is your function, minimizing it is basically at this point, right? And here we say that df dx is equal to 0, right? So we're going to find where the derivative is equal to 0, and that may or may not be where we have the minimum of our distortion measurement. Here we will say that it is, because it's pretty obvious, and I'll just prove mathematically where the distance is equal to 0. I mean, the derivative is equal to 0. So to start off, we say, okay, so what we can first start with is say that this is equal to xn minus mu k transpose xn minus mu k, where we assume that this is a vector. And we know that the derivative of this is equal to 2xn minus mu k. So what we do is taking a partial derivative with respect to mu k of our d, which is the distortion measure of x and mu, we will see that it is equal to the summation of n is equal to 1 to n k is equal to 1 to k, gamma nk, 2 xn minus mu k times -1 because of chain rule, because we're trying to take the partial derivative with respect to that one. And now we're going to set this equal to 0. And so what we're going to get is that since this is a constant inside of our summation, because it's just a number, we can just kind of bring it out. So we get n is equal to 1 and k is equal to 1 k. And then we will get that gamma nk xn. We will just remove the 2 because we divide 2 from both sides afterwards, and we remove the -1 because we'll divide by -1 on both sides afterwards. This is equal to the sum of n is equal to 1 n. And here we will see that actually this gets cancelled out because for whatever mu k is not equal to that specific k, we will get that it zeroes out. So we also remove this. And then we get that mu k will be in this expression. And then we can denote the number of points in cluster K to be the summation of n is equal to 1 to n gamma nk as nk. So now we get that we have n mu k is equal to summation of n is equal to 1 to n gamma ynk xn. And now to finally divide by both sides, oh, this is k by the way, we get that mu k is equal to the summation of n ynk xn divided by nk. So just to recap, we have that mu k is equal to the summation of n is equal to 1 to n xn gamma ynk over nk, right? And if you look at this, it makes sense because this is actually the mean of points in cluster K.
Okay.
Or to expand, we get n is equal to 1 and xn gamma nk over the summation of n is equal to 1 and gamma ynk. Okay. So this is where the name k-means came from, because right now we're calculating the mean, and intuitively we calculate the mean of all the points to minimize our distortion measurement every iteration. However, we don't know this gamma nk, right? The problem is that we don't know gamma nk, right? Because if we knew what points belong to which cluster, then we can finish this problem in one iteration by just calculating the mean, right? Like if some points on our grid were already colored when we got it to be like, there are some red points here, right? There's some yellow points here, right? Then it's pretty obvious that what we just need to do is to compute the average of these points and then compute the average of these points, and then we're done, right? However, we don't have that because our data point is not colored. It looks like this. So then a computer won't really be able to know like which one belongs to which cluster until we assign our supposed gamma nk, right? But we have a quick solution for this. Remember that we have right here we assign points to its closest cluster, right? So that means that we don't really know, but we can guess by saying the points that are closest to its cluster will be in the cluster, right? So what we do is we kind of draw an imaginary circle. Say this is our first center and this is our second center. So let's say this is 1, this is 2, right? we can draw an imaginary circle around the clusters like this, right? And then we can see when the circles collide, they generate this decision boundary, right? And whatever is on this side is going to be red, for example. So we will shade this side red. And then we will shade this side yellow because it looks closest to the example above, right? So then we can just automatically assume that the points in the red region are going to be in the red cluster, and the points in the yellow region are going to be in the yellow cluster. And this is like the underlying way to solve this kind of problem. Even though this is probably not the best way to do it, this is the closest way we can get because we're missing the cluster memberships inside of our data. So this is one of the most basic algorithms for machine learning, especially for the unsupervised version. This algorithm is actually backed behind a very powerful mechanism called expectation maximization. And it's actually a lot more complicated than this. Just to kind of give a brief teaser about how it's different from the general case, we can say that YNK is not either 1 or 0 now. We can say that YNK is equal to a probability that XN is that Zn is going to be in the kth cluster, given that we know that its respective point in Xn. So now it's going to be some value between 0 and 1, and we don't really know which one. I mean, it doesn't have to be between 0 and 1 if it's continuous. But in this case, it's discrete and it's a multinomial distribution. So we can then take this to a further level of complexity and solve for that, which may be more expressive and give us better clustering. And it will also give us distributions that are not entirely circular. So in this example, you can see that this is completely circular, right? And that leads to some very linear decision boundaries. But what if we wanted this cluster to look like this, and this cluster to look like this? Well, we can't really represent that with our current machinery. So we will discuss the rest of it next time in Gaussian mixture models and expectation maximization.